before I start explaining exactly what is the Bleichenbacher attack and so on, I'm just going to give a quick recap on what is RSA encryption. And again, this is an attack on RSA encryption, not to mix that with RSA for signing, right? So RSA encryption has three functions, the API. If you look at that from a black box perspective, there's a gen key pair function, which checks maybe a security parameter, right? And pretty much generates a private key, a public key, and a public modulus. All right, this is also called the public exponent, and this is called the private exponent. And the security parameters just tells us what n is going to be, and n is usually what we call the key size or something like that. This is kind of an abuse of the language, and it's nowadays it's going to be something like 2048 bits. All right, the second API is the encrypt API, of course. This is an encryption algorithm. And encrypt takes a message and it takes a public key. And the public key is going to be E and N. And encrypt pretty much gives us M to the power E mod N. This is how you encrypt, right? This is the ciphertext. Now, this is asymmetric encryption, so somebody can decrypt somebody with the knowledge of a private key. So we take the ciphertext and we take the private key and the public modulus. What we do is that we raise the ciphertext to the power D mod N, and it's pretty much equal to M E D to mod N, which is pretty much M mod N. Right? We get back our plaintext. I'm going to assume that you know how RSA works in theory, because I'm not going to explain that in this video so that we can save some time. First, know that there are lots of different algorithms to encrypt with RSA, and even to sign with RSA. The most famous one is called PKCS v1 version 1.5. This is actually an RFC, a request for comment document, that specifies RSA encryption and RSA for signatures. And we're just going to talk about encryption attacks. Of course, it's not the only standard, because Bleichenbacher or Bleichenbacher, depending on how you pronounce it, found an attack in 1998 on this RSA encryption. Also, we call this attack PB98 or the million message attacks, just because it takes a million messages. Because of that, there was a new standard that came out called PKCS 1, but an update 2 point something. There is 2.0, 2.1, and 2.2. I'm not sure what's the difference, but there is something new called OAEP for RSA encryption. And it's kind of an update, and it has something called an integrity check, you know, kind of like AES-GCM or HMAC and things like that, but for asymmetric encryption so that you cannot tamper with ciphertext, and we'll see why this is important to counter the Bleichenbacher attack. But it was found that this OAP scheme was not really, the security proof had some mistake. Shoup found that, I don't know when, but he tried to correct that with something called OAP plus. Somebody came also and invented OAP plus plus with another proof of security, but I believe none of them have standards and people continue to use OAP. And finally, there is also something called RSA CHEM, key encryption mechanism, or simple RSA. And this thing has the most simple analysis and proof of security, and it's perfect, and pretty much is the best algorithm we have. except that nowadays, if people use RSA for encryption or signatures, people are going to use this old scheme, just because of legacy and devices, old devices that we still need to support. So that's a problem because, again, we have the Bleichenbacher attack, which is not a pure attack in the sense that we have mitigations against that we can implement on PKCS 1 version 1.5 for RSA encryption. The problem is that the mitigations are not easy to implement, even though the new RFC says that it's an easy mitigation. They are not easy to implement, and Bleichenbacher, the 1998 attack, also called actually a padding oracle attack on PKCS 1 version 1.5, has been rediscovered again and again and again and again, even this year in 2018, 20 years after, with the robot attack. So this is something that people keep discovering because people keep using this scheme, even though it's broken and it's not easy to mitigate. Just another note, padding oracles attack are not only something against RSA. You might have heard of Vaudinet's attack, a padding oracle attack against CBC, the CBC mod. It's a very different attack because it's an attack against symmetric ciphers, and so it's very different from what we're going to look at today. So in the first part of this video, I'm going to explain the attack of Bleichenbacher against RSA encryption with PKCS 1 version 1.5. And then I'll be talking about Menger's attack on OAP, which is a new scheme with the integrity protection. And finally, I'll be talking about how we can exploit these attacks in TLS or SSL. All right, so how does PKCS 1 version 1.5, and I'm sorry, there is no better name for that, encryption works? So first, if you want to encrypt a message, you need to pad it. And my message M is going to be a padded message. And the reason we pad messages are numerous. It's to circumvent a lot of different attacks, which I'm not going to be talking about in this video. So that's for a different video. And pretty much what we start our message with is with 00, the byte 00. This is hexadecimal, okay, and null bytes. Then the byte number 2. And then we're going to fill our message with bytes that are non-zeros. All right. Then we're going to have a 0 byte, and then we're going to have the message to be encrypted. And in TLS, what we encrypt is a secret called a pre-master secret, and it's usually of 48 bytes. But of course, it doesn't have to be this thing, it could be anything, but in TLS, it's a pre-master secret of 48 bytes. So this is what I'm going to talk about because at the end, I'll be talking about how to exploit it. There's more details to that. This part here has to be greater or equal to 8 bytes. And in TLS, there are some bytes here that are supposed to be set according to the specification, but this is really out of the scope of that video. So we have this padded message, and it's the exact same size as the modulus n, right? Because we work modulus n. We raise n to the power e when we want to encrypt it, mod n. So that's why we are the same size. And actually, n here could be of size, you know, it's something like 256 bits, perhaps, which is, or actually completely equal to 2048 bits. But we actually don't know if the first bit here is set, if we have a full bit here. We have no idea, right? It could be, for example, the first, if we have hexadecimal, we could have just one bit set. And this is why we need to have a null byte here. It's not very important. You just need to remember that this is PKCS 1, version 1.5 padding. This is how we encrypt a message, or actually this is how we pad a message before encrypting it via this formula. Now, if we want to explain Bleichenbacher attack, I have to explain what is the property that RSA has. It has a homomorphic property, which is pretty great in itself, but for RSA it's not that great. We don't really want that. What is this property? Pretty much is the fact that we can choose any number, let's say 3 for example, and we can encrypt it, and we can multiply that to a ciphertext. This ciphertext is what? Is the padded message m to the power e, right? Mod n. And this is basically equal to what? 3 times m mod e. What have we done here? We have this ciphertext C, and by multiplying it with the encryption of something else that we know, we obtain the encryption of 3m. C was the encryption of m, and we tempered that C to be decrypted to 3m. So that's pretty bad if we want to do an attack on RSA, which is pretty much what Bleichenbacher is going to use. This way where you can temper ciphertext to change what is going to be decrypted as. But sometimes these homomorphic kind of encryption schemes are very useful, and you will want to use them. This is theoretical as they're usually not very efficient, but think about cloud computing. We don't want to upload all of your data to the cloud, some cloud provider. Instead, you want to encrypt it and upload it. But once you encrypt it, you still want the cloud to be able to search through your data or to compute on your data. And because homomorphic encryption schemes allow you to compute on encrypted data, the cloud can compute whatever it needs to compute on your encrypted data and then sends you back the result. And like that, you don't have to do anything. You can send encrypted data to the cloud and you don't need to trust the cloud. It's a very interesting property, but not for schemes where we don't want it, like RSA, and this is what we're going to use in our attack. If you look at the Bleichenbacher paper, which I encourage you to do, you'll see that it has a step 1 called the blinding step, a step 2, which has a part A, a part B, and a part C, and you'll see that the part A is usually not really used. Well, actually no, the part B is not really used, but part A is indeed used sometimes. And finally, step 2, and finally a step 3, which will be very quick. Step 1 is not really used because we already have a ciphertext that we want to decrypt, which decrypts to something that is PKCS compliant. All right, so we already observed that and we want to decrypt it, so we don't need to use step 1. But I explain later when step 1 is useful. Step 2 will pretty much try to find an I such that the encryption of I times C mod n decrypts to, what does it decrypt to? To I times m, right? Mod n. And we want these to be PKCS compliant. PKCS compliant, again, means that it starts with a null byte, then 2 bytes, then a bunch of whatever, but not 0, then a 0 byte, and then the secret. So what we need to do this attack is that we need an oracle. Let's call that the Bleichenbacher oracle. And when we give it a ciphertext, any ciphertext, so for example, this ciphertext here, this tempered ciphertext, tells us if it is PKCS compliant or if it is not a valid ciphertext because it cannot be decrypted and it doesn't look like this thing. All right, this is our oracle. We have a server, decrypts the ciphertext we send it, and we have a way to modify ciphertext and tampering with them. And it tells us if it looks like this thing, or if it doesn't look like this thing. If it does look like this thing, what does it tell us? Well, it tells pretty much that it needs to be bigger than 0, 0, 0, 2, and a bunch of zeros. And it needs to be smaller than 0, 0, 0, 3, and a bunch of zeros, right? By definition. So our I times m, but m is smaller than what we'll call 3b and is greater than what we'll call 2b. And what is b here? I'm using b because this is what the Bleichenbacher paper used, but b is pretty much a 0 byte here and 0, 1 here and a bunch of 0, 0, 0, 0, 0. So that 2b is basically this thing and 3b is basically this thing, right? This is the upper bound and the lower bound of our message. What is this mod n here? Well, by definition, it is any k times n for k in the integers. All right, so this is interesting, and it actually allows us to, once we find such a message, such an I, and actually what we could do is naively take I equals 2 and then try 3 and then try 4 and increment it. And actually in Bleichenbacher's attack, every time you have some clever tricks to find correct bounds on where to start to not naively increment from 0 and be faster. And we'll find such a ciphertext that is PKCS compliant, meaning that we have this equality, which gives us a range on M. What is the range? Well, it's easy to compute, right? And actually, in Bleichenbacher's paper, there's a minus here instead of the plus. So I'll use the same thing. It doesn't change anything, actually. And so we can write here plus Kn over I, smaller than M, which is smaller than 3b plus Kn over I. And again, on Bleichenbacher's paper, you might have a 3b minus 1, but this doesn't really matter. So I'll just omit it just for simplification. And here we have a bound on M. So it's interesting because in the beginning, we had this line of numbers. We had 0, we had n, and maybe, and this is not at scale at all, right? You have to just picture things as I'm saying, but maybe m was part of this range of numbers, which is between 2b and 3b. And now we found a new ciphertext that tells us that m is also in this range. But we don't know k, right? So what can we do? We can say that k can be equal to 0 or 1 or minus 1 or 2, etc. And we're not going to go to the infinity. because if we calculate the bounds, which I'm not going to do, this is left for you, we can easily see that this value for k doesn't make any sense. We're going, it would place us somewhere here, which is completely out of our original bound. So we're just going to take values of k that make sense, for example, 0 and 1 or something like that. And if we use k here for 0 or 1, what we're going to have is two different intervals. We're going to have m belongs to A union with B, right? The interval with this formula with k equals 0 and k equal 1. This is just an example. And pretty much what's going to happen is that k equals 0 will give us a range on M, which is somewhere, somewhere, for example, here. And if we use k equal to 1, it will give us a range, for example, here. And this is really an example. We have no idea what it's going to give us. And what it means is that it's for sure in this range or in this range, right? But it's also for sure, for sure in this range, right? The original range. So what does it tell us? It means that it's at the intersection of these new ranges and our old range, which is either here or here. And like that, we just decrease the range of our message. Now we know that it's either in this part or in this part. We now have two ranges. So now step B is going to be used if we have multiple ranges. Here we have two ranges, but often you won't have two ranges and you will often have just one range and you will just use step C. And every time when you want to just reduce and take the intersection of these ranges, old ranges and new ranges, everything will happen in step 3, and then you will go back to step B or step C. Step C is kind of clever because it pretty much says that we realize that, again, I'll write this formula, but when we have IM, mod M, is smaller than 2b or greater than, smaller than 3b, this tells us that we have this bound here. Right? And pretty much it sounds like if we double I, then we can halve this range, right? The range here, if this was like 2I, for example, would be halved in 2, right? So Bleichenbacher's intuition is to say, all right, I want the next I, let's call it J. Actually, in the paper, I is equal S, so the new I is SI. I want it to be equal to 2 times the previous I, which is called SI minus 1 in the Bleichenbacher's paper. And by replacing this formula, it gives us a bound on K. We also know that if we want IM, or here I'll call that SI now with the Bleichenbacher's formula, minus Kn to be PKCS compliant, then we have to bound SI, and we can do that easily by doing 2b plus Kn greater than SI, 3b plus Kn over M, right? And we can also reduce that, reduce that to 2b plus kn si, or 3b plus kn, and this is pretty much this value here is smaller than this value here, so this is true, right? M mean being the minimum value of m that we currently have. Let's say that we have 0 and right now our range for m is this, with here being m mean and here being m max, right? And here this thing is greater than m, so this whole thing will be bigger, and so we have a bound on SI if we want to have a PKCS compliant message here. And this is just an explanation of how you are able to find these bounds in the Bleichenbacher attack. And then pretty much what Bleichenbacher does is that it uses this trick here to look for an SI, which you can multiply by m, right, with our previous technique to halve the range of m. And pretty much you can imagine here we find a new range with our technique. A new range is here. Then it means that m is really in the intersection of the previous range and the new range, which is only here. And once you have only one possibility here, once your range only have one item, then you know you found m. And this is pretty much the Bleichenbacher's attack. I went pretty quickly over the concepts, but you can read the paper, get an intuition from it, understand the analysis from the paper, and understand why it takes so many messages. If you're looking at the paper, you'll see that the really hard parts are to understand how your bounds work modulo n, and this is why we always have to replace mod n by plus k times n with k in the integers, and that's why we have several ranges. The second hard thing is to find different bounds, because you could be looking for I times m naively by choosing I equals 2, then 3, then 4, but this is not very fast, and often in Bleichenbacher's paper you will use tricks to have bounds on I, so you can go more quickly and faster to finally find the value of m. In TLS, and let's say TLS 1.2 or 1.1 or 1.0 or whatever, but not TLS 1.3 because they don't use RSA encryption anymore to do a key exchange. You have a client and a server, right? And they communicate with each other. And if the client, there's a client hello, and the client says that it supports the RSA key exchange, and the servers choose to pick this RSA key exchange in a server hello, then the client will encrypt with the server public key, right? This is the server public key. Will encrypt a message called the pre-master secret. I already said that it's 48 bytes, and the server can decrypt it, and then they can start encrypting the session with it. Here, if we were in the middle, if we're a man in the middle, we would intercept this message, and we would then send it to, actually send it to, what am I doing? Send it to the same server multiple times, like it's our own handshake, but we will modify it. We'll do I to the power C, or what am I saying? 2 to the power C, 3 to the power C, right? We would send different encryptions. We would tamper with the ciphertext. We would do our attack using this server as an oracle. And we would finally decrypt C, obtain the PMS, and we would either passively decrypt the connection or actively man in the middle it. The actively man in the middle it is more interesting here because the client might support different schemes, and usually they would support something like defillment or elliptic curve defillment, and the server would usually prefer these algorithms compared to RSA for different reasons, and I won't talk about that here. To prevent that, what we do when we're man in the middle in the connection is that we receive this message and we remove all of the cipher suite and we just include the RSA key exchange. Like that the server only replied with the RSA key exchange. At this point, we have to actively man in the middle this thing to finalize the handshake, because at the end, the server will send a finished message which authenticates the whole transcript, and the client will be able to detect it if some things were modified from his client hello. It's important to correctly man in the middle this thing before the handshake can be finished, if we downgraded the client. Against this attack, the server can pretty much do one thing. It can just pretend that everything is going correctly. So the server will check what we send it when we do the attack here, and check that what we're saying it decrypts to something that starts with 00. If it doesn't start with 00, it's not going to reply with an error, because otherwise we have an oracle. We know that the PKCS version 1.5 of the message is not correct. That's the oracle. Instead, it's not going to tell us anything, and it's just going to continue to check the next byte, which is supposed to be a 02. But it doesn't matter if it's not 02, because it's just going to pretend and going to continue checking the other bytes, which are not supposed to be 0. Then this byte is going to be 0, and then it's going to extract the PMS. Doesn't matter if these are not correct in the decryption, because if it stops at any point before it finishes checking everything, then we might have a timing attack because it returns too early. At the end, even if this is incorrect, the server has to continue the handshake and pretend that everything is correct. To do that, the server always generates a random PMS. And depending on if this is correct or not, it will use the random PMS or the correct PMS. And even this choice between the random PMS and the correct PMS needs to be done in constant time, otherwise you also have a timing attack. So if you do a simple if message is PKCS compliant, then use PMS, else then use the random one, then we have a timing attack as well. So this is very, very hard to mitigate in reality because of all these different constant time issues. Actually, I can look at bare SSL from Thomas Pornan, which is a TLS implementation, probably the best TLS implementation out there, and look at how they're doing the RSA decryption. This is a mirror on GitHub. This is not the official repository, but there is this bare RSA SSL decrypt, and you can see that it checks if the decrypted payload has the first byte set to 0, the second byte set to 2, then a bunch of bytes sets to not 0, not equal to 0, then 1, 0, and then the PMS of 48 bytes, the pre-master secret. And all of these EC here, or NEC, or EC, are done in constant time. And as you can see, it doesn't stop if this is not equal to 0. It just continues on, continues, and continues, and only at the end returns. So even if the first byte is not 0, it's going to continue and not return early and maybe leak the fact that by returning early, the first byte was incorrect, and then we have an oracle that the PKCS is not compliant in this case. Later on, we can see that after decrypting the pre-master secret here, it makes a random pre-master secret. It always makes one, right, with this function. And it does a constant time copy of either the PMS obtained or the random PMS based on X, which is the result of this thing here, if the PKCS is compliant or not. So as you can see, everything, every single operation here is constant time. And if we have a fake, if you have a, if you have a wrong ciphertext, if we cannot decrypt it and we cannot recover the PMS, we still generate a random one and we still pretend to continue the handshake to give no information whatsoever to the attacker.